that just means our matrix has constant coefficients. So this would have constant coefficients. This would have constant coefficients, but this does not have constant coefficients because cosine depends on time. Usually we're going to talk about homogeneous equations, or homogeneous, I think that's how you say it. And that means that our equation will not look like this, but they'll look like this. So this b term will go to 0. So now we want to look at the structure of our solutions. Let's say this is our equation, y prime equals a y, and our solutions are going to be in the form y of t equals e to the lambda t y, or sorry, not y, v. So our v is going to have the property, well, let's go ahead and just take the derivative of this to find y prime. Y prime is going to equal lambda e to the lambda t v. So plugging this back into this equation, we get lambda e to the lambda t v equals a times e to the lambda t v. So this gives us because this is a linear transformation, because it's a matrix, we can pull this constant e to the lambda t out, and we're left with this. Lambda e to the lambda tv equals e to the lambda times av. Canceling e to the lambda t from both sides, we get, and switching sides, we get av equals lambda v. So v is what we call an eigenvector of the matrix. And that just means when we put v into a, our output is a multiple of v. And v ends up being multiplied by lambda, where lambda is an eigenvalue of a corresponding to v. So our goal then is to find the eigenvalues and eigenvectors of a to find these solutions. So it turns out for an n by n matrix A, we get n solutions of this form. And the whole solution, the total solution, is going to be, if these solutions end up being y1, y2, y3, all the way to yn, our total solution is going to be y of t equals c1, y1, and sorry, these should be vectors. So c1 y1 plus c2 y2 plus all the way to cn yn. So we need to find our eigenvalues and eigenvectors to go ahead and find all these solutions. So to find the eigenvalues, you have to solve this equation by subtracting lambda v to both sides. If you factor out v from this, we get a minus lambda times the identity matrix times v equals 0. And if we take the determinant of this, that means that this determinant has to equal 0. And this will give us, this equation is going to be called the characteristic polynomial of A. So we solve this for lambda, and we should get n lambdas, or n different eigenvalues. That might not always be the case, but that's our goal. And we'll deal with the case when that doesn't happen later. And then to find the eigenvectors corresponding to the eigenvalues, we look at this equation, a minus lambda I v equals 0, using our given lambdas that we found just earlier. And this ends up being a process of finding the kernel of this matrix, a minus lambda I. So solutions are going to look like this. We might have y1 equals e to the 2t times 1, 1, and y2 equaling e to the negative t times 2, 1. In this case, our lambdas, our eigenvalues, were 2 and negative 1, and our eigenvectors were 1, 1. So we'll call this lambda 1, lambda 2, and v1 and v2. So v2 is 2, 1. So this is what the solution was for y prime equals negative 4, negative 3, 6, and 5 times y. So our total solution, y is going to equal c1, y1, and sorry, y1 and y2 should have arrows on top. So this is c1, y1 of t plus c2, y2 of t. So that gives us y equals c1 e to the 2t 1, 1 plus c2 e to the negative t 2, 1.